Hello. So we are going to consider another example. Now we'll consider five typical macroeconomic variables. Real data, it is also real data from 62 through 2015, quarterly data. And the five variables we have are GDP growth rates and industrial production growth rates and consumer price index inflation rates and unemployment rates and 10-year treasury bill rates. So these five variables are like some of the most important economic variables in macroeconomics, right? And we are particularly interested in their relationships, like how they behave together when there are five variables. The problem is, so we learned how to handle two variables. We learned how to calculate the covariance and the correlation coefficient when there are two variables. That was not that difficult. But when there are five variables, what can we do? For now, there is no simple way to extend covariance to five variables, right? So from two variables to five variables, the regression is most natural way to do that, but it's coming in the next chapter. But now, what we are going to do is we have to think of each pair one by one, pair by pair. So, like that means I need to calculate the covariance between GDP growth rate and the industrial production growth rate, and then recalculate the covariance for GDP and inflation, and then GDP and unemployment, and then GDP and interest rate. So like that, we have to just choose each pair of variables and calculate the covariance or the correlation coefficient and repeat that for different pairs. So that is actually built in on Excel. So we are going to use Excel again to handle that. So this is the data. It starts from 1962 and there are five variables: GDP, real GDP growth, industrial production growth, inflation, unemployment, interest rate. And it runs from 1962 until the last quarter of 2015. You may calculate like the covariance or the correlation between these two guys, or this and this, and then this and this, and then this and this, and then this and this, like this. You can think about 10 different combinations, 10, 15 different combinations, many different combinations of a pair of variables. But on Excel, you can do it one step. That's coming here. Here, data, excuse me, data analysis. And so on the data tab, I clicked data analysis button, data analysis you see here. And then on the table, there are covariance and correlation. Let me try covariance first. If you choose covariance, then you first have to click input range. Input range is from here to here, including all the five variables, and from the first to the end. And I included the variable names, so I have to check this, labels in the first row. And the variable is grouped by column. Each column is one variable, right? And then click OK. Then you get a matrix, 5 by 5 matrix. And these numbers are copied in the slide. So let me explain what this is. This is called the covariance matrix. That is, say, 7.66 is the covariance between industrial production and GDP growth rates. And say 0.18 is the covariance between this guy and this guy. So for each cell, for each number, you can find what corresponds to the column and to the row. So then those two variables covariance is exactly in that cell, right? In that way, you can interpret this. Then what is the in the diagram? By the way, why is this side empty? Upper triangles is empty because this is like in this entry, in this cell, there should be the correlation, covariance between GDP and treasury rate. But the same thing can be found here. So you don't need to repeat 0.18 here, and minus 0.72 must be here. So you don't need to repeat the same number twice, so they are empty. And then finally, the diagonal terms are variances. So 11.33 is the covariance between GDP and GDP, which is the variance of GDP, right? So earlier I told you the variance is a special case of the covariance. So the diagonal numbers are just special covariances, which we call the variance, right? And I explained these numbers are corresponding to the covariance of these two variables, column-wise and row-wise. And then, so this table, this matrix, collects all the possible covariances you can calculate from the data. When you have 5 variables, you have this many covariances to calculate. And then you can just read one by one. So for example, if you look at the first column, there are 4, except for the variance itself, there are 4 covariances capturing relationship with another variable. And you can see that GDP has positive relationship with the industrial production, which is natural, right? And interest rate, 10-year interest rate is also positively correlated with the GDP, right? So now you have to explain if it makes sense macroeconomically. So industrial production, the more you produce, of course GDP should be higher. And if your GDP growth rate is higher, that means your future expectation should be higher, so the interest rate must be higher. So they are positively correlated. But and when GDP growth rate is higher, there will be fewer unemployment, so unemployment rate must be lower. So it is natural that GDP and unemployment rate have a negative relationship. However, the problem here is GDP and the inflation rate. Usually, we learned the inflation goes up when the economy is good. So this negative correlation is a puzzle. Yes, it is a big puzzle. It was a big puzzle like many years ago, like many decades ago. At that time, so many macroeconomists tried to explain why they are negatively correlated. It's at least counterintuitive. So from there, many new theories have been developed, like to explain that negative correlation. For example, rational expectation theory for the inflation was one nice explanation of this seemingly negative correlation coefficient. Anyhow, that's macroeconomic discussion, so I'm not going to go in detail, but you know how to use this matrix, right? Now, now the problem here is you can tell whether it is negative or positive. However, you cannot compare the absolute values. Say, for example, the treasury bill rate is positive 0.18 and industrial production is positive 7.66 with GDP growth rate. But how can you compare 7.66 to 0.18? The answer is no. You cannot compare them at all. You cannot say 7.6 is stronger than 0.18 because their units are different. They are not standardized. So their scales are different. So there is no point of comparing them. They just have very different scale units. Then how can we handle that? Simple. You need to calculate the correlation coefficient. Can you do that? Imagine how you can calculate the correlation coefficient between inflation rate and the unemployment rate. Using those numbers, try to guess what is the answer. Okay? So the answer is D. Because remember, the correlation coefficient is defined as the covariance divided by 2 standard deviations. So covariance between inflation and unemployment rate, unemployment rate and inflation, their cross-section is here, 0.48. That's the covariance. And then you divide it by the standard deviations. Inflation's variance is 8.26 and unemployment rate's variance is 2.57. So these two are variances. So you can calculate their standard deviations by taking the square roots of those variances. So D is the standardized covariance, which is the correlation coefficient. Okay, so I explained it, and as a result, you can calculate the correlation coefficient based on this matrix. And if you do that for each entry, you can transform all the entries into the correlation coefficient. Then it will return the correlation coefficient matrix. Correlation matrix. You can do the same thing on Excel. Like back to the original data. What I'm going to do is again, Data tab, Data Analysis button, and now choose correlation instead of covariance. Correlation, if you click it and do the same thing, select data area and label, okay. Then you get a new matrix. This matrix contains correlation coefficients. As you can see, all the numbers are between plus minus 1. Back to the slide, you can see the numbers are 1 on the diagonal elements because correlation between GDP and GDP itself should be 1 because they're identical. They must be perfect correlation, right? They are the same. If you compare same variables, then automatically the correlation must be perfect. So that's why the diagonal elements are always 1. But non-diagonal elements are meaningful because they have strength. They imply strength. Now you can compare them. For example, the correlation between GDP and IP. GDP and IP is 0.49 and compare that to GDP and treasury bill rate, 0.02. So now you can compare. Industrial production has stronger relationship with the GDP than the treasury bill rates. Okay? So now you can compare the strength of the relationship. And of course, the signs mean the direction, so signs are easier to interpret. And then let me give you this question. Which pair has the strongest negative correlation? Okay. So there are 1, 2, 3, 4, 5 pairs. 1, 2, 3, 4, 5 pairs. And of course, among them, when you compare them, the correlation coefficient closer to -1 is stronger. So that is, among these 5 negative numbers, minus 0.36 is closest to -1. right? And this corresponds to unemployment rate and industrial production rate. So industrial production and unemployment, C is the answer. When industrial production increases, more employments, which is very natural. Okay. So exactly this is what I explained. Okay, this is how we use the correlation and the covariance and the correlation coefficient when you have multiple variables at the same time. So simply, there is no way to handle more than two variables at the same time by the covariance or the correlation coefficient. But you can make a table of them to read, to see, and compare how the relationship changes across variables. Okay, in the next video, I will give you another example, which is maybe the most interesting one because it is about financial portfolio. And there I will give you more examples and new data, real data to that example. Okay, see you there. Bye.